world beneath our feet and the sky above our heads are alive, constantly shifting, reshaping our planet. Sometimes those shifts become dramatic, even terrifying, reminding us of nature's raw power. Today, we're taking a deep dive into what happens when these powerful forces collide with human life. Natural hazards.
Exactly. And we've got some really interesting material here from PMT Education and a geography revision guide. It's packed with insights, everything from earthquakes to, tropical storms.
Right. And our mission today is to unpack what natural hazards truly are, how they impact us, and critically, what we can maybe do about them, especially as our climate keeps changing.
Yeah, and let's kick things off with a clear definition, because this is really where the human story begins, isn't it? A natural hazard isn't just any naturally occurring event.
Okay.
It's one that specifically poses a direct threat to a human population. It causes loss of life, injuries, significant damage to vital infrastructure.
So the key is the threat to people.
Precisely. The core insight here is that, say, an earthquake or a volcano on a totally uninhabited desert island. Well, that's just a natural event. It only becomes a hazard when human life or property are actually at risk.
Okay, let's unpack that with a real tragic example. The 2015 Nepal earthquake seems like a stark illustration from our sources.
It really is. It killed nearly 9,000 people, injured thousands more, destroyed countless homes, buildings.
A huge negative social and economic impact that.
Absolutely. Clearly classifying it as a natural hazard, not just, something that happened geologically.
Okay, so first let's literally go deep into the very ground we stand on. Our sources tell us that many of the most dramatic hazards start beneath the Earth's surface. So what exactly is behind those powerful earthquakes and volcanoes?
What's fascinating here is the theory of plate tectonics. It's actually a relatively recent scientific understanding, only widely accepted for the last maybe 40 to 50 years.
Really? That recent?
Yeah. It explains how the Earth's rigid outer crust is split into these vast sections, like a giant jigsaw puzzle. And these plates aren't static, they're actually floating on the semi-molten rock of the Earth's mantle.
Floating? How does that work?
Well, slow-motion convection currents within that mantle cause them to move. It's incredibly slow, but constant.
Like giant conveyor belts under the crust.
Exactly. And the material even touches on newer theories that sort of refine our understanding of this movement. There's slab pull, for instance.
Slab pull.
Yeah, where the weight of a dense plate that's diving beneath another subducting literally drags the rest of the plate down with it. And then there's ridge push, which happens at mid-ocean ridges.
Okay.
Here, you get buoyant magma rising, creating a raised ridge, and then gravity basically pushes the slabs across apart. That leads to seafloor spreading.
So we've got these massive plates moving around. Are they all the same? Or are there different types?
Good question. No, they're not the same.
Yeah.
We have oceanic crust and continental crust, and they differ significantly. Well, oceanic crust is typically shallow, maybe 5 to 12 kilometers deep. It's relatively young, geologically less than 200 million years old, and quite dense, mostly basalt.
Okay, dense and young. And continental.
Continental crust is much deeper, averaging 40 kilometers. It's significantly older, often over 1,500 million years, and less dense, composed mainly of granites.
That's dense.
Exactly. And this fundamental difference in density is absolutely crucial. It dictates what happens when these different types of plates meet.
Right, so given this constant slow-motion ballet, the real drama must unfold where these plates actually meet. So what is happening at those boundaries?
It entirely depends on how they interact, you see. There are 3 main types of boundaries, and each one creates its own brand of geological fireworks, if you like.
Okay, 3 types. Let's break them down.
First, we have destructive boundaries. This is where plates are moving towards each other.
Collision course.
Right. And if a denser oceanic plate collides with a lighter continental plate, that denser oceanic plate will dive beneath it. That process is called subduction.
Subduction.
And that creates deep ocean trenches. But also, the immense friction and heat generated as it descends cause the oceanic plate to melt. That forms magma, which then rises and causes violent volcanoes and powerful earthquakes on the surface.
Wow. And mountains.
Yes, exactly. This collision also crumples the continental crust upwards, forming vast fold mountains. Think of the Himalayas. That's where the Indian and Eurasian continental plates collided.
Incredible. Okay, so that's destructive. What's next?
Second, there are constructive boundaries. Here, the plates are moving apart.
Pulling away from each other.
Precisely. Magma rises up from the mantle to fill the gap created by the separating plates. This forms mid-ocean ridges and volcanoes.
Different kinds of volcanoes, though.
Generally, yes. The lava at these boundaries tends to be runnier, what we call basic lava, so you get more effusive eruptions, building broader, gently sloping shield volcanoes.
Right, less explosive maybe. And the third type?
And finally, we have conservative boundaries. This is where plates are sliding alongside each other.
Grinding past each other.
Exactly. They often get stuck as they grind past, building up immense pressure. When this pressure is suddenly released, bang! Violent and frequent earthquakes.
But no volcanoes here.
Generally, no, because you're not really creating or destroying crust in the same way. No melting or magma rising like at the other boundaries. The most famous example, of course, is the San Andreas Fault in California, the North American and Pacific plates sliding past each other at different speeds.
Okay, so that slow movement beneath our feet causes all this drama.
It really does. The core insight here is that the seemingly imperceptible, slow movement of these giant plates defines the most dramatic and powerful geological events on Earth.
So understanding the mechanics is one thing, but our sources strongly emphasize that a natural event only truly becomes a natural hazard when it poses a threat to people.
Exactly.
Which raises a critical question. Why do some populations suffer so much more than others, even from similar events?
That's key. The probability of a hazard actually affecting a population, what we call hazard risk, is heavily influenced by two main things: exposure and vulnerability.
Exposure and vulnerability. Explain those a bit.
Well, exposure is about location, basically. Someone living right on the slopes of an active volcano is obviously much more exposed, at higher risk, than someone 100 miles away. But vulnerability is about the population's ability to cope. So a population with poor access to healthcare, limited infrastructure, or, say, inadequate rescue services is far more vulnerable. That significantly increases the overall risk.
And our sources list several factors, social, environmental, economic, that really ramp up the severity, don't they?
Absolutely. Things like poverty are critical. It often forces people to live in riskier areas, like unstable slopes prone to landslides, because they have no other choice. And they simply lack the resources to build stronger homes or respond effectively after something happens.
What about farming?
Farming is another big one. The fertile soils near volcanoes or on river floodplains are really attractive, providing a livelihood. But it puts people directly in harm's way when eruptions or floods inevitably occur.
In cities.
Urbanization, yeah. High population densities concentrate risk. We saw that tragically in the 2010 Haiti earthquake. Lots of people, often in poorly constructed buildings, in one place. And, crucially, climate change is a major factor now. It's making many areas more prone to hazards like floods, droughts, even famine, which just makes existing vulnerabilities even worse.
So given how exposure and vulnerability shape the risk, when an event does strike, the impacts themselves aren't just one single thing, are they? It's almost like a scale, immediate versus long-term.
Indeed. The material differentiates clearly between primary effects and secondary effects. Primary effects happen immediately due to the event itself. Think of damage to roads and buildings from the ground shaking in an earthquake. Direct impact.
And secondary.
Secondary effects result from those primary ones. So fires sparked by broken gas lines after a quake, or widespread landslides triggered by the shaking, or tsunamis generated by offshore quakes. And often these secondary effects can be even more devastating and last much longer than the initial impact.
That brings us to a really powerful comparison in our sources. Two major earthquakes. One in a high-income country in HIC, and one in a low-income country in LIC.
Yes, the contrast between the 2010 Haiti earthquake, a magnitude 7.0, and the 2011 Japan earthquake, the Tohoku one, which is a much larger magnitude 9.0, it's truly fascinating and sobering.
So Haiti, the LIC, magnitude 7.0, what were the outcomes?
Haiti suffered an estimated 220,000 deaths. Massive infrastructure collapse, widespread displacement, and then huge problems afterwards, like looting, disease outbreaks, largely because aid struggled to get through effectively.
And Japan, a much stronger quake, 9.0 plus a tsunami.
Japan, the HIC, despite that significantly more powerful event and the devastating tsunami, saw about 15,800 deaths. Still tragic, of course, but vastly different numbers. And Japan demonstrated incredible resilience and a capacity for recovery that was just worlds apart from Haiti.
So this comparison isn't just about earthquakes, is it? It's a stark revelation about preparedness.
Absolutely. The core insight is that for natural hazards, preparedness, planning, and prediction are not just safety measures. They are fundamental determinants of human survival and national resilience. They can mitigate even catastrophic events. Japan excels here. Haiti, sadly, did not.